And then not to mention that many materials that are used, also chemical reactions, they are constantly being improved, like the photoresist itself. There is the whole science behind in order to also improve the photolithography. The lecture, we're going to see the CMOS process steps. So let's have a look on some overview that brings us to the process steps. What we can see here is the overview of the general topic on the integrated circuit fabrication. What we have already covered previously is the beginning of the front end of production. We have front end and back end. In the front end, we were looking at the wafer preparation, the importance of the purification of silicon, growing into crystal, and then preparing the wafers. So the silicon has to be sliced and polished. Today, we are going to see what happens later with the wafers. So on the wafers, specifically, we're going to focus on the CMOS planar technology, because there are also different things different processes, what we can do with the wafers. There are different types of wafers, not only silicon. So this is the specific focus that we have here. After that, we have the third step that is called wafer sort, where the electrical testing on the wafer level is done in order to say already on the wafer which chips or parts of the die are going to be somehow damaged and not working properly. If we eliminate those and don't package, then it's significant saving in the cost. Parts 4, 5, and 6 belong to this so-called backend. So everything that happens towards the packaging and testing on the package level of the chips. That means first the assembly, then we have burn-in. That means rejection of some chips that would fail otherwise in the early stage of their lifetime. This is done by applying temperature, stress, and also in the normal operating condition or slightly elevated power supply. Then after rejection of those chips, we are left with the parts which will have very likely lifetime that can be predicted. And then there is the final test, which actually tells us also which of those parts have survived the burn-in and can be shipped to the customer. So the steps 3 through 4, 5, and 6 will be covered later, a little bit quickly, I think. There is not enough time in this lecture to cover everything in much detail. The whole time of this part, it's focusing on wafer processing. So far, when we were talking about the MOSFET transistor, we were thinking of the structure that you can see on top. So there is the substrate, the implants for drain and source. Then there is the gate with which is made of conductor with an insulator in between. Here the dimensions you have to also notice are a little bit exaggerated because the size of the transistor channel length, we are talking about nanometers, tens or hundreds of nanometers or even micrometers. Whereas the thickness of the oxide ranges from 1, 2 nanometers to maybe 20 nanometers. So it's not to scale, this drawing. It's just conceptual. But so the upper picture is more conceptual. The lower one is a little bit bringing us closer to the reality, because what we are going to see is that actually there are those real, with the implants, it doesn't end up with just terminal drain source gate, but really there is the metal, the physical connection, and we are interested of how this doped islands and the inner operation of the transistor leads us to the outside, where actually we can take the device, sit down in the lab and measure it, or in the actually more real world put it in the application interconnected with other devices. To get to this stage, to have a more physical overview, we will have a look on the different microfabrication processes that can, in the right sequence, in the right composition, they will lead us to this final product, which is ready for dicing and packaging. So we have several categories of the microfabrication processes. The category of layer pattern definition, which is solely the lithography process, although we can have different types of lithography. Typically, it's the photolithography with ultraviolet light used in semiconductor fabrication. Then doping, that can be done by diffusion or ion implantation. Very often, actually, we're talking about the mixture of those two. Then removing layers. We can have a CMP, so-called chemical mechanical polishing, which is used for planarization or etching. And also very important category of forming new layers. And here we have two basic components, the chemical vapor deposition and physical vapor deposition. In the first one, we have growth of many thin film layers of different types and composition. In the second case, it's specifically used for depositing metals. So what we are going to do today, we are going to go through a fabrication steps to produce simple inverter with just two metal layers. And this will cover all of those steps. What maybe it doesn't cover, but also I would like to speak a little bit, is the epitaxial growth, because when we get to advanced devices, then also it's important to have an overview on that. So what we need, we have the starting material is substrate of very lightly doped p-type silicon. What we need is n-doped layer of for N-well, then high doped layers for the terminals, source, drain, and bulk for both P and N-type transistor. And then the creation of the gate oxide polysilicon contact layer and the two metal layers to connect the inverters. You have to also be aware that this is very simplified view on the process, because in the modern fabrication we have many more layers of metals, first of all, but even as far as up to the production of the transistor, it's a very simplified view. So one of the very important processes is deposition of the silicon dioxide layer, because it happens at many process steps. We have two types of oxides, dry oxide and wet oxides. You can see the chemical reaction in both cases. So either the reaction is with oxygen or with hydrogen. And in the oxygen, we call it slow. So slow, it takes longer to create certain thickness layer. In case of the wet oxide, it is faster. In terms of the speed of the growth, also the crystallography that we were talking about, the orientation of the wafer, that's very important also, how on the orientation on how fast the growth takes place. And also in several other process steps, I will be also highlighting the importance of the speed and quality, that it doesn't happen the same for different crystal orientations. We have different functions of the oxide layers. It can be used, first of all, as the gate oxide, which is the very benefit of using silicon-based technologies, that we have this silicon dioxide almost for free if we expose it to just our ambient environment, we get oxygen. However, together with hydrogen, it's maybe also not controlled process of growth of such oxide, but we need to have a very strictly controlled growth in case of gate oxide to make sure that the properties of the transistors are the same across the whole wafer and from wafer to wafer. Other functions include insulation between devices. So also thanks to the fact that we can have the easy oxide layer, we can separate devices electrically. It can be used as a masking layer, which you will see at most process steps that we're going to see here. The silicon dioxide has their role. And also, there is different type of passivation that is used in between the metal layers, which is not silicon dioxide, it's silicon nitride. And the silicon dioxide has, because different materials also have different mechanics, different stress and response to temperature. And in order to have integrity in terms of this mechanical strength, if we had the silicon nitride directly on silicon, that would not be good. And this silicon dioxide forms a nice intermediate relief layer to make sure that also mechanically the structure remains stable. So if we think about the gate oxide, which of those processes, dry oxide or wet oxide, will be better suited to grow gate oxide?
The dry oxide.
And that's correct. Why?
Because
do you think?
It's slower and probably more controlled, or
yes, very good. That's right. So if we can do that slowly, and we only need thin layer, we have much better control. Of course, the duration, how each processing step takes, it's the cost of machines. In the production, everything is translated to cost, so that's something that we always have to keep in the back of the head. But in this case, that's right. The slow oxide is used to grow the gate oxide, and in addition, it has to be very pure oxide. If there is some contamination of hydrogen or any other atoms, that creates problems either on the oxide, inside the oxide, reliability problems, defects at the interface between silicon and silicon dioxide. So we have started the processing by simply applying this oxide. Then there is the photoresist dispense, and this is going to be used for photolithography. So what we would like to do is create an opening to make our N-well implant. And inside this N-well, the P-type transistor is going to sit. There could be a separate lecture about photoresist. There is the whole art of the chemistry behind. It's also the thickness, the quality. It all influences how well you can do the photolithography. So I will just stop at that, saying we can have negative or positive photoresist, and if illuminated with ultraviolet light, such photoresist, it's easy to remove from this area. So then there will be removal of the photoresist, there will be removal of the oxide, and then we will create opening window to introduce implants of the N-type for the P-type transistor. But slowly, before we get there, I would like to stop at this really important process, photolithography. It happens for each layer. We have the patterning. We need to define the shape of each layer, and this is the photolithography that is responsible for that. So there will be a set of masks, as you can see here conceptually, and they define this geometry. The mask has to be very, very robust, because the same set of masks we use many times to process many wafers. And it's partially transparent. The transparent part is the silicon dioxide. And it's covered also with chrome film to be opaque in the places where we don't want the light to come through to hit the photoresist. In case of This cost of the masks is one of the very important contributors to the fabrication of integrated circuits. And in case of institutions like the university or smaller research centers who develop circuits for research purposes and prototyping, then there are also business models offered by several silicon brokers where there is so-called multi-project wafer, where the cost of the mask is shared between several contributors, and then it costs just a small amount of money. You don't repeat lots of transistors to have a big number of chips, but at least it's possible to produce even with smaller number. On the whole wafer, there are several shared projects like that. So that's just to say that it's we're talking about millions already, for around €1 million for some older process technology nodes. And the more we scale the process, then even for single layers, we might need several masks, like 2-3 masks to produce single layer. So that's a topic not to be neglected. And then we have the wafer light from the photolithography scanner, which is focused, and it's focused on a single reticle area. So the mask doesn't cover the whole wafer, but just a certain area. Of course, the mask is also much larger than this area. Like that, we can actually be able to produce the mask that has to produce later much smaller features on the wafer. And the process is going through scanning. So that's also a little bit of a bottleneck. That takes quite a long time, the whole process of photolithography. Many other processes, actually most process steps that we're going to discuss later, they do treatment in one step for the whole wafer, like the silicon dioxide deposition. It happened in a single treatment for the whole wafer, whereas here we have this scanning. The important topic in terms of photolithography is the resolution. It defines how small features we can produce on the wafer. And the line width is what we would like to be small, to have fine shapes. For example, the gate of the transistor. We can see that there are 3 contributors that all 3 have to be minimized in order to reduce the size of this line width. The first, most obvious, is the wavelength of the light. Secondly, there is the gap between the mask and the resist, and also the photoresist thickness itself. And this is because there are also the effects of diffractions that influence how sharp is the image at the edge. So up until now, or let's say down to 7 nanometer technology nodes, the wavelength that was used is 193 nanometers. And it's quite amazing that it was even possible to do 7 nanometer feature size with this wavelength. So what somebody said, that it's like trying to read Braille with your elbow, because the difference between those 2 numbers is so incredible. And in this case, the way it's done, there are special techniques for photolithography, which exactly explore the optics, and with 3 to 4 masks, the single layer can be formed. But at the same time, we have to remember the scaling of the process means also we add more and more metal layers for the interconnections, for solving the problems with power dissipation, and that explodes the number of masks that is used. So just maybe the name, so that you can also look up, if you are interested, for the techniques that are used to reduce the feature size with such a large wavelength of light. So for 7 nanometer node, this 175 nanometers required using either the phase shift masks, which exploit the interference with the set of masks which are shifted in phase, and the productive interference can magnify the image at certain spots, or multiple patterning and multiple etching, which is also, in both cases, they are basically complex techniques of dealing with light. And if not ultraviolet 175, or actually 193, sorry, wavelength, then what are what alternative we have? So since recently we have in production, starting this year, 5 nanometers, 2022 for those that listen on the video. That will soon change. There is extreme ultraviolet, 13.5 nanometers. This is already used by Samsung, TSMC, and Global Foundries. Other methods which are being investigated, explored, and probably all can be quite promising. It's the balance again of the costs and also where the companies decide to invest. X-ray photons, so it's much shorter wavelength. The problem here is how to create masks which are opaque to X-rays in the areas where we don't want to expose. So to really create a clear pattern between the binary illuminated and not illuminated. Electron beam, that can be also used for patterning. However, it's similar like photolithography by the nature. Here even worse, it's not illumination of the whole area, but it's really scanning the spot of electrons. Imagining to do that through the whole wafer, it's really very time consuming. And below 20 nanometers, what was also demonstrated is the nano imprint lithography. I don't know currently how small feature size it's possible to do, but it's something like really physical contact with a material like photoresist or similar, something that can be later we can remove partially we can leave and then continue etching on that. The problem here is that we have really the physical contact between the so-called mask or the pattern that it's imprinting and the wafer. So the mask itself is being used up. So it's also in terms of the lifetime, it's not very easy. Having said that, with the 13.5 nanometers, it's also not very easy. So the powers that are used that are used in the processing are very high. These wavelengths are very easily absorbed by even in the air. You cannot even imagine how it's even difficult to describe how the whole optical system is constructed so that we can actually have the mask that are also working through transmission. So this has to be very high power, and because of that, the masks also easily wear out. There is a link. I leave in the slide. I think it's also impressive to see how these extreme ultraviolet systems, how they are operating, and to have some more details on that. For the photolithography process alone, we have this set of masks. And one more challenge that is also behind the processing of the silicon wafers is the alignment of the masks. So there are special markers for alignment. They are not maybe anymore looking like crosses, but cone shapes. And again, there is a science of optics and mechanical engineering, of course, to be precise. There are several angles where the epsilon and x-axis as well as rotations have to be aligned. And only once the alignment is done, this is done for each single reticle over the wafer, then the patterning can take place. And this is like one more contributor to the precision, how well we can define the features. So we have successfully gone through the photolithography process. We have the opening in the photoresist. This has been removed chemically. And then there is the silicon dioxide, which is a barrier between outside and the silicon if we want to introduce doping, even if it's very thin. So what has to be done? It has to be removed. And this is done by the process called etching. There are two types of etching, talking generally, isotropic and directional. So isotropic, it is purely chemical. We have a certain chemical means of certain liquid that is hopefully selective, so it has to be carefully chosen so that it's etching the silicon dioxide but not silicon. That's ideally what we would like to have. However, what you can also see schematically in the picture, that there is this rounded shape. The problem is that it's, as the name says, isotropic. It works similarly in all directions. So when we want to have the straight walls, it doesn't happen exactly so straight. So again, here, the silicon dioxide thickness, the thinner it is, the better in that case, because we can be more precise. This is a relatively cheap method, but it has this obvious disadvantage of not being very precise. If we need to be precise, we use dry edge that is based on plasma. And in that case, we can operate more directionally. Of course, this is more expensive equipment. We have the RF source that generates plasma. We have a pressure chamber applying the gas, and everything that makes it more expensive than the wet etch with liquid chemicals. Nevertheless, similarly, in both cases, what we have is this selectivity. So the type of the ion species that are bombarding, in this case, the surface, has to be chosen for selectivity between silicon dioxide and silicon. And I would like to demonstrate also how this dry etch works in the most sophisticated form of the deep reactive ion etch. So this is, in this example, actually it's used not to etch the oxide, but to remove also silicon, which is sometimes used, for example, we will see in the advanced processes, silicon via. So that goes through the silicon if we want to connect two dies without external bond wires, but with bump at the bottom, so to have very dense interconnection. This is, for example, done. And for that, we need to have a ratio of, like the via should be as narrow as possible, because then we have lower capacitance, less parasitics, and also less area that it consumes. It's really difficult to make something that is narrow and deep. So there are also some limits to that. That's one other challenge that it's also interesting to point out. But basically, if we need something like that, what's being done is in two phases. First phase, with the RF source, the plasma is introduced. We have the ions, which are directed towards the surface, and they are bombarding the surface, physically removing the atoms which are at the material that is being handled. In addition, there is a chemical process involved with that, so depends what ions are being selected, then this might be more or less efficient. But what happens in the end, we can see that the atoms of the base materials are being evacuated together in a gas form. Another phase that is used in this deep reactive ion etching process is introducing of a different gas in a separate phase, which is forming this shown in the green color layer. So it's a Teflon-like layer which protects the surfaces and the top of the chip or of the wafer from being too much damaged. So at the same time we have the directional bombardment, but also the protection of the sides, so that's to make the process even more directional. And after etching, what we are left with is, this is done with wet etching, the simplest cheap possible thing for removing the masking layer of silicon dioxide. We have the opening, and now we can use this opening to introduce N-well for the P-type transistor. And this is done by doping. Doping can be done by diffusion or ion implantation. And we will have a look on both processes and see that also with ion implantation, the diffusion will be belongs there as well. So diffusion, from that perspective, we can say it's more important. It's a natural process that occurs. The higher temperature, then the diffusion will be easier. So what is being done? We have the predeposition of the donor or acceptor ions. In this case, we want to have the N-type doping. It's done in the form of gas or by also ion implantation. And then there is the drive-in, the high temperature process. And what we can see here is the conceptual characteristics of how the doping concentration propagates into depth depending as a function of time. So with time, the ions are migrating towards the substrate, deeper in the substrate. So it's not a step profile that we actually have. When we were analyzing the operation of diode, we were always assuming that it's a step junction. So in reality, we can see from this diffusion distributions, doping concentration as a function of depth over time, 3 dimensions, that it's never going to be step with that. We can come closer to step with ion implantation, which is followed by diffusion. So again, there will be some smooth transition between the regions. It's possible also to have diffusion from limited source if the dopant ions are deposited as a thin film on the surface. That also happens, and then we have to realize that the doping concentration at the surface will, as in the upper case, the doping concentration at the surface is always the same, and then it decreases towards the deeper of the bulk. In case of the limited source diffusion, so we have just deposited the film of dopant ions and we diffuse, then with time the doping concentration at the surface will be decreasing and decreasing. The second doping technique is the so-called ion implantation. We could probably spend, again, 20 minutes discussing how the machine is constructed for that. We have to have the generator of the ions, the accelerator, also selector, so that we only end up with the ions of the type that we want of specific energy that it's intended in the system. So we have this generator of ions that hits the surface of the wafer. And similarly, like in case of diffusion, where there is the silicon dioxide mask, the dopant ions are not going to penetrate into the substrate. They might contaminate this silicon dioxide, but it will be later removed. So that's why we don't care too much. And so we have this pretty local depositions of the ions. And there is the whole interesting area of the crystals and solid states that also define and interaction of those ions with the solid state that defines that how the doping concentration will look as a function of depth. So it's always interesting to know what this profile looks like, regardless if it's diffusion or ion implantation. And here, depending on type of the dopant atoms, which is also the true thing for diffusion, the temperature and type of the ion, they will influence the profile. And here we can clearly see also is that the peak depends on what is the type of the ion, not to mention that the energy will also play here a role. So this can, we can go to much more details again into this process, but this is like just an overview I would like to give. With that, it's also possible to create buried layers, which is used more and more in the advanced devices, for example, for optical detectors. Very often what is necessary to have some buried layer in order to optimize the charge transport, charge collection properties for the sensors. So it's really important to have the tool where we can select by optimizing the parameters. Unfortunately, there is an important drawback of ion implantation. It damages the silicon. So silicon is made of atoms that are arranged in certain structure. We already know about that. And if an ion of certain mass, of certain energy, bombards the surface, it will damage the crystal. So in order to recover the original shape, what is being done is we have the high temperature annealing after ion implantation, where after that process, most of the atoms find back the position in the crystal structure. But also, what's important, it's so-called the activation that it's also necessary for the dopant ions to also accommodate themselves in the silicon structure. So it's not only the process of repair, but also just creating space for the ions in the crystal structure. In terms of the orientation of the crystal, again, it's important which orientation we choose, because in case of both diffusion and ion, the depth of the propagation will be also influenced by this crystallographic orientation. And what is particularly dangerous for what can happen in ion implantation, if you would have a 3D model of a larger silicon structure, you can find those as apps online, and you rotate it, you can find certain orientation where you can just see through. There is like opening between all the ions, and it's a repetitive pattern, so it goes to the other side of the wafer. Maybe not that bad, but ions can have this so-called channeling. There can be channeling effect where the ions in an uncontrolled way just penetrate deeper, and it's difficult to predict where they stop. And in order to be able to predict it, there will be certain tilting implemented in the positioning, so that with the tilting we are able to predict, okay, this channeling effect will be avoided. So especially bad it is for the surface 111 wafer. So what we can see here is phosphorus and boron, which are different types of dopants. One is acceptor, one is donor. And what we are doing now, in this step where we are adding the N-well implant, so doping big island for the transistor, but inside it we are going to add P and N type implants for the drain and source and for the bulk. So what we have to also, it's quite intuitive, realize it's how this is done. Basically, it's like overwriting, dominating certain ions so that the overall balance comes to more P or more N type, and this is how it's done. What is important to also remember, until now, we had the process steps that are high temperature. There will be the topic of temperature budget. Every next step can be only lower and lower temperature, because if we, let's say, have later a high temperature process step, it might destroy, put out of control everything that we have done so far. And diffusion and the ion implantation are high temperature processes. So diffusion is because the temperature is facilitating also diffusion, increased temperature. In case of ion implantation, we need to also define the profile by diffusion, but most of all, it's very high temperature process step because of the activation. We have to get very close to the melting point of the silicon. Maybe not 1,400, but around 1,000, maybe above 1,000 Celsius degrees. So we end up with the nice annual island. The next step is gate oxide deposition. So here we're talking not about the oxide mass that was about 0.5 micrometer thickness. There will be very thin oxides of lower than, sometimes more, sometimes less, about 10 nanometers, but even as small as 2 nanometers or less. So it has to be very well controlled. With dry oxide. And next step is deposition of the polysilicon. And then we're going to leave the polysilicon and the gate oxide only in the places where we want to have the transistor gate. Everywhere else we remove it. For both layers, silicon dioxide growing, polysilicon growing, but also many other layers, the silicon nitride that later comes between metals, also epitaxial layers. Chemical vapor deposition is the process that is the king here for producing those nanometer thin film layers. And so I would briefly want to describe some important features of that. These are processes very often at high temperatures. And the uniformity of temperature is also what we would like to achieve here. Then, so we have the chamber where these processes are being done. We have the source material entering the chamber with the wafers that are there. It's deposited on the surfaces, so actually all around them. And then there is chemical reaction that takes place there. So we had the examples of chemical reaction in case of the dry and wet oxide. So similarly for any other deposited material, also there will be chemical composition of the materials chosen in such a way that we have this reaction taking place. And the heater that is around, I say it's around, it has to be round chamber so that the temperature can be controlled and uniformly deposited. And one more feature that is really nice in this process is that we can handle several waveforms at the same time. What you can see also here on the picture, there are several substrates. So this is, even if it takes a long time, because putting it to certain high temperature, and also the gas is introduced at certain speed, so that also to control the process, maybe it will be very slow. But despite the length of the process, the handling of several substrates makes it much better. So again, we have the photolithography step to define the place for the gates. And what we want to do is to etch the polysilicon and silicon dioxide for gate everywhere where we don't want to have this gate. So we are left with this structure after the mentioned processes. And the next two steps will be, again, ion implantation in order to add the drain source and bulk, two different types. So we have to do this again in two steps. What is peculiar is that we have done first the implantation of N-well, and we didn't do then the P+ doping for the bulk contact of NMOS and the drain source contact of PMOS and the respective N+ complementary, but we have gate first. Do you know, it's not by a mistake, do you know what is the advantage of doing this? So in terms of defining very accurate length of the transistor, it's much better because we have this self-aligned process. So we have originally, maybe that was done that way, that we had first the implants, what you can see on the right-hand side, then there was deposition of the silicon dioxide, and then the gate conductor, which used to be aluminum, low temperature process. So with this low temperature process, we were not able to do first aluminum for the gate and then implantation. But what we can do now, and it's much better, is first do polysilicon. It has very high melting temperature as well as silicon dioxide, and then use this gate with polysilicon on top as mask for self-alignment of the gate. So like that, we know that these two implants that come, 2N+ on both sides of the gate, we don't have to then try and target with the gate on top of those two implants to exactly match the channel length. And we also don't have problem of uncontrolled diffusion. We can much better control where the implants are located. So I will not rewind the slides again through here. That was basically what we have done so far. We have done the self-aligned implanting of the N+ and P+ regions for source and drain, as well as not self-aligned, but under certain control as well, contacts for the bulk, for the P-channel transistor and N-channel transistor. So from now on, we're going to lower temperature processes because now what we are interested in is depositing of the metals. So again, there is a deposition of the layer for masking. And what happens already here, what we can see is that if we don't do anything, we would not have even structure, because we deposit in the chemical vapor deposition, we deposit equal thickness all over the wafer, but sometimes where there is the gate, then there is a bump. And then every time we deposit metal layers, then there would be more bumps at different places, and we would get problem of not being able to control what happens with the stability, mechanical stability of the structure. So it's something we cannot allow for. And because of the importance of the step for overall reliability and integrity, this planarization step is something also to be included here. So we take the wafer, we can say upside down, but against the polishing plate surface. Both are rotating, and this chemical mechanical polishing, because just mechanical would not be able to give us such a small roughness, which is in the range of 1 nanometer. So that's the precision, how we can control the smoothness of the surface. So at the same time, there is the chemical reaction, and continuously there is the so-called slurry delivered. So it also runs off the surface due to the rotation. But basically, that's how this is being done. And in the end, we end up with the nice flat surface, flat and smooth. And the next processing step, photolithography, defines the patterning of where we have the contact. So first, between the silicon and the first metal layer is called contact. Then between all the following metal layers, the connection is called via. So here, even though they are made quite similarly. So next, we have this deposition of the contacts. And we don't just fill it in with metal, because that's might not work well. First, there is the liner. It has several functions. So first, this will be the type of metal that will have low properties of, and will be unlikely to diffuse deeper into the surface. So what is not allowed here, for example, is to use copper, because copper would very much, it has the properties that it easily propagates through surfaces, and the contamination with copper or any metal in our close to the active devices, that's not something that we want to have. Second property is that also when we then put another metal which will be having a good conductivity, typically it's aluminum. This aluminum also needs to attach well to the surface so that we don't have some voids. The feeling it's very uniform and proper everywhere. So this good attachment is another thing why we use this lining. So lining is done with chemical vapor deposition, thin film, slow process, but it's worth it. And next we have again polishing, so that's to remove it from the top surface. And now we have sputtering, which is the deposition of the first metal layer. So the metal layer and fills the vias and also covers the surface. What we need to do next is to remove the metal from the surface. So the sputtering, the deposition of the metal, done physically, so there is no chemical reaction that is primarily involved, and always some chemistry happens, but here it's primarily the physical process, is done like that. We have a substrate, then there is a target, and then the target is the material that we want to deposit. But it's solid, how to remove it and deposit in the place where it's intended. So there will be introduced ions in the chamber, and then with high field, the ions will be accelerated, hitting the target. Probably it's here, the distances are a bit exaggerated, so in one direction the target has to be closer to the substrate, and the acceleration distance has to be relatively large in order to give the ions certain energy. But in the end, the target ions are kicked out and deposited on the liner on the substrate. So the next step is to make openings in the metal, or rather leave the metal only where we want it to be, because if we look on the wafer, most of the area will be without this metal than with the metal. And so again, through the photolithography, we leave only metal in the defined places. Everywhere else, it's removed. Then we have, again, deposition. Here it's written silicon dioxide. On other slide, it was written silicon nitride. It's typically silicon nitride that is being used here as the insulation interlayers. Every step, we have planarization. And after the first metal layer, now it's quite repetitive. Then we have the, again, liner to produce, so first etching to produce place for vias to contact the second metal layer, liner, then sputtering again, and creation of the second metal layer. Then another patterning to just leave the metal to where we want it to be. And this is the, let's say, what we have already, the process with two metals. The only thing we need to do is passivation on top of the metal, and the metal too is opening. It's only left in the places on the chip where we actually intend to place the bonding. Very often there will be additional layer of metal also added, so that it will be extra thick metal. So after the passivation, we have the final opening, and this opening is where we want to bond. So in this case, that would be the input to our inverter. So this is, as I already said, you can guess it's very simplified. There are, in the production of the integrated circuits, we will have some additional processes, for example, scales technologies. They introduce again, I will speak about it next time in the next lecture, but already let me uncover some things. So the advanced technologies, they are not using anymore the polysilicon, but metal gate. Also, aluminum, it's not enough. There are also copper metallizations introduced, but there were some technological challenges to be able to do copper. And also in reality, so what we have is additional metal filling. So let's say we would have very scarce use of metal too, just in several paths. And that's not okay for design rules in the manufacturing. In order to ensure that the planarization requirements can be met, we have so-called dummy filling pattern. And that means once the whole product is designed, we have defined the layers, their positions, then everywhere where the metal density is not as high as it should be, there will be those dummy metal areas introduced. So these are a couple of nuances that we have to know about adding the complexity. Also for the modern technology nodes, so starting from 50, 40 nanometers, where we have also metal gate, in order to improve mobility of charge carriers in the channels, we will have some additional liners in the gate. It's even difficult to find all the details about the recipes of how it's done, but what we know is that it's a very complex process, so gate forming and with applying appropriate stress on the channel in order to influence the mobility of the charge carriers. So that is also part of the process steps that have to be involved. And then not to mention that many materials that are used, also chemical reactions, they are constantly being improved, like the photoresist itself. There is the whole science behind in order to also improve the photolithography. So this is the summary of the microfabrication processes that we have covered. So once again, the layer pattern definition, doping, removing layers, either physical, chemical, or purely chemical with etching. Actually, deep reactive ion etching also has some physical part to it, so it cannot be simplified like that. And forming new layers, so chemical vapor deposition, part of which is the thermal oxidation. It's listed separately because it's just important process, but it's also chemical vapor deposition, physical vapor deposition, and what has not been covered here, but I would like to spend just one more minute talking about is the epitaxial growth. So it's also a special case of chemical vapor deposition. And this is to form a new layer. And just one slide showing the concept. So we have the substrate. It's semiconductor crystal. In this case, it's silicon, but we can also imagine epitaxy on different types of substrate. And then with the introduced gas, we have atoms of a different material, also semiconductor, or the same semiconductor silicon, so homoepitaxy or heteroepitaxy, which in high temperature, when the process is in high temperature, then the ions will continue aligning following the crystal structure. So in case of the homoepitaxy, we have silicon, but it could be, for example, that we had a wafer that was highly doped, and then we're adding almost pure silicon. So the reason to do that is it's very expensive, so normally it wouldn't be really interesting. But there is a reason behind, and to add the uniform layer of different doping of the material, and then on this layer of epitaxial silicon, then we build transistors. That has advantage because the lower in the substrate, where we have high doping, then the conductivity is good. We have, if there is some substrate current, there will be low voltage drop. So for avoiding clutch-up in the circuits, that's one trick. It's an expensive trick, but that's to use epitaxial wafer. Another type of epitaxy called heteroepitaxy is where we have different ions of a different element. So what's most commonly used in CMOS integrated circuit fabrication is that we use germanium. So in order to have a good heterojunction transistors, the germanium layer makes a much better junction. And there will be devices which have the layers of germanium or silicon germanium mixture. Even for controlling mobility in scale technologies, also germanium is used in the channels of either type transistor, also depending if it's holes or electrons mobility, the story might look differently. The problem with heteroepitaxy is that we have two ions of different elements of different atomic number, for whom the characteristic constant of the crystal is a little bit different. So that creates a little bit of stress on the surface, and actually that's the reason why for creating this stress in the modern technologies, in the MOSFET transistors, the germanium is used is exactly for the stress reason. But normally it's also a challenge to deal with these additional stresses. So one more feature for epitaxial growth, as I have highlighted with some other processing steps, the crystallographic orientation. The speed of the epitaxial growth will be different depending on the orientation, because also the number of bonds per unit area depends on the orientation. So that's the simple generalized relation. So with that, I would like to close the part of the silicon CMOS wafer planar processing. We have the basic overview, and I wish that it's now the tool for you to go to the last part in this lecture. We will, of course, end up through the back end, but then go to the advanced processes and also the overview of the challenges in the fabrication. So with all the information so far, I think that you can enter the most interesting part, in my view, of this lecture. Okay, thanks.
You're the signal in my static hum, a perfect match we've overcome. Wires cross, but we still